a 20 mm by 20 mm square beam. So we have a 20 mm by 20 mm square beam is 2 meter long, is supported at the ends A and B. Fails when a point load of 400 Newton will applied at the center. So this condition is given. That is, we have a simply supported beam, one center load is given, size of the beam is given, and it fails, means we can calculate the maximum bending stress from the given figure. The UDL per meter length that will break the cantilever of same material means the value of the bending stress maximum for this beam and for this cross section, which is 40 mm wide and 60 mm deep, is 3 meter long. What is the value of UDL? You have to find out. So in this case, we have to find out the value of UDL, and the length of the beam is given is equal to 3 meter, and we have a cantilever beam. As per the square beam is considered, the square beam has a maximum value of a bending stress either at the top fiber or bottom fiber. So we have the neutral axis here, and top fiber and bottom fiber at the same distance equal to C. So the distance of C from top fiber and from bottom fiber is same as equal to 20 divided by 2. So we have value of C is 20 divided by 2, that equal to 10 mm. And the moment of inertia will be equal to 20 to the power 4 by 12. Now because of a symmetrical loading here, the reaction at A, AY is same as equal to 400 divided by 2, that equal to 200 Newton. Similarly, the reaction at B is also equal to 200 Newton. So let's construct here the shear force diagram. We have vertical load at point A is equal to 200. So you have to move vertically upward by a force equal to 200. So this value is same as 200 Newton. No force is acting between A to C, and therefore the shear force diagram is remain constant. So no change in the shear force diagram. Then suddenly a load of 400 Newton is act at point C. So you have to move downward by 400 Newton. Finally, we will attain a value equal to minus 200 Newton. Between B and C, there is no change in the load, so shear force is remain constant, and with a reaction at By, which is equal to 200, will end at 0. So we have positive value of a shear force between A to C, and is a constant value is equal to 200. So this one is our shear force diagram, and we have negative value between B and C, that equal to minus 200. At point C here, we have the change in the sign of a shear force. So maximum bending moment, area of the shear force diagram is same as the change in the bending moment. As far as the bending moment at A is considered, the bending moment at point A will be 0. Bending moment at point B will be also equal to 0. Since we have a sign change here, the bending moment is maximum at point C. If we have a rectangle, then we have a triangle in bending moment diagram, and this value corresponds to maximum value of bending moment, which one is nothing but the area of the shear force diagram, that is 200 Newton multiplied by 1. So this value is same as 200 Newton meter. This one is the negative area is minus 200 into 1, so you have to close to 0. So this one is a standard bending moment diagram. So we know the maximum bending moment equal to 200, and we have maximum value of a bending stress sigma B maximum is same as equal to bending moment M multiplied by C divided by I. Bending moment is equal to 200 is Newton meter is 10 to the power 3. Constant C is equal to 10 divided by moment of inertia is A to the power 4 by 12, that is 20 to the power 4 by 12. So we can calculate here the maximum value of bending stress, and the same value has to be used in the second case. So we have maximum value is equal to same as 150 megapascal. So when you are using a cantilever with UDL equal to W, and we have given a rectangular cross section, width is equal to 40, that is the value of B is equal to 40, and the depth D is equal to 60. In this case also, the top fiber and bottom fiber will have maximum value of a bending stress because they are equidistant, and here the value of C will be same as equal to depth divided by 2. So here we have C is equal to depth divided by 2, that is we have 60 divided by 2, which is same as equal to 30 mm. When we have a UDL, then we can convert the UDL into point load, and the maximum bending moment will always occur at point B. So let's show here the equivalent load. This value is same as equal to WL. WL multiplied by L by 2 will be the maximum bending moment at point B. So this one is L by 2. So bending moment maximum is at fixed end, that is at point B. And this value of a bending moment is same as equal to W into L by 2. So we use again the same formula here. We have maximum value of a bending stress is equal to M multiplied by C divided by I. Maximum value you have to use the same value equal to 150 megapascal because material is remain same. M is replaced as W, that is a UDL into L square divided by 2 multiplied by constant C. C value is equal to 30 mm. So we have 150 equal to UDL is W, L is equal to 3 meter. So we have 3000 square multiplied by C is equal to 30, and his whole thing is divided by 2 times of I. So we have 2 times I is equal to BD cube by 12. So we have 40 multiplied by 60 cube of it, and 12 will shift in numerator. From this we'll get the value of UDL come out to be 0.8 Newton per mm. We need to find out the answer per meter length. Per meter length you have to multiply by 1000. That will be equal to 800 will be Newton per meter. A massless beam has a loading pattern as in the figure. We have simply supported beam. Support is given at A and C, and over a span from B to C we have UDL is equal to W, which is equal to 3000 Newton per meter. I to B distance is given as 2 meter, B to C given as 2 meter. The beam is of rectangular cross section with a width is equal to 30 mm and the height is equal to 100 mm. So this time we have given the width B that equal to 30 mm and the depth D is equal to 100 mm. So for this rectangular beam we have neutral axis is exactly at D by 2, and the maximum value of the bending stress will occur either at the top fiber or at bottom fiber. So this value is equal to same as equal to C, and the value of C is same as D by 2. So in this case the C value is equal to D by 2. C is nothing but the distance of the top fiber or bottom fiber, which one is maximum. This time both fibers are equidistant. So 100 by 2 that equal to 50 mm. In the first case the maximum bending moment occurs at which location we have to find out, whether it occurs at B or from a certain distance from A. So these are the choice given here. Second part we have to calculate the maximum magnitude of the bending stress. Once we know the maximum bending moment, we can calculate the maximum bending stress using the formula sigma B max equal to M, which one is maximum multiplied by C divided by I. Now to find the location here, you have to construct the shear force diagram and the bending moment diagram. For that one we must know what is the reaction at A and the reaction at C. Let's say we have vertical reaction at A is equal to AY and the vertical reaction at C is equal to CY. To find out this reaction, we'll take the moment of all forces about the point C, and that moment we'll take as a clockwise moment is a positive value and will be equal to 0. To find out the reaction here, temporarily we'll convert the UDL into equivalent point load, and the value of UDL is same as equal to W multiplied by L, which is equal to 2 meter. So exactly at the halfway we have to show here the equivalent load that equal to W into L is 3000 multiplied by 2 meter length. So this one is the equivalent point load is W into L, and this load from B will act at distance equal to 1 meter. So from B this load will act at a distance equal to 1 meter from point B as well as 1 meter from point C. Equivalent load you have to just take out for finding the reaction only. Don't use the equivalent load for drawing the shear force diagram. So the moment of AY above the point C is clockwise. Total perpendicular distance between A and C is equal to 4 meter. Moment is clockwise, so we'll use the positive sign. We have vertical reaction is equal to AY, perpendicular distance equal to 4. The equivalent point load here is 6000 at a distance equal to 1 meter and will act in an anti-clockwise direction. Is minus. Equivalent load is equal to 3000 multiplied by 2 and the perpendicular distance is 1 is equal to 0. So we have 6000 divided by 4, that will be equal to 1500. So we get a reaction AY is equal to 1500, that will be Newton. Then to find out the other reaction CY, we'll use the summation of the all forces in vertical direction, vertically upward positive, must equal to 0. In this case, the value of AY is acting vertically upward is positive, value of CY is also vertically upward, and 3000 into 2 is negative value. So we have minus 3000 into 2, which is the equivalent point load. This sum must equal to 0. Here AY is equal to 1500, this value is 6000, 6000 minus 1500. So in this case, we get the value of CY is equal to 4500 Newton. 6000 minus 1500. So AY value come out to be 1500 Newton and the CY value come out to be 4500 Newton. Now we are ready for drawing the shear force diagram. We'll start our constructing the SFD from the support at A. We have AY is equal to 1500. So we'll move vertically upward and we'll show this force is equal to 1500 Newton. Between A and B there is no shear force acting, so this value will remain constant. So we'll show here the shear force is remain constant, so you have to draw here horizontal line. Then the total value here is 3000 multiplied by 2, that equal to 6000. Previous value is 1500. 1500 minus 6000, you will get 4500. So 4500 is slightly larger value here, so we'll get here minus 4500. And you have to join this point with this point. Since we have a rectangle here, you have to join by straight line. Finally, at point C, you have to close the SFD diagram because we have reaction is same as equal to 4500. Now we observe at this point here. At this point, the value of the shear force will change the sign. Let's mark this point equal to E point, and at this point we are expecting the maximum value of a bending moment. That you can calculate either from the left side or you can calculate from the right side. So we can calculate this value here using this area, that is a quick area. But for this one we should know what is the distance here, that is this distance suppose is equal to x, then B to C distance equal to 2 meter. So the remaining distance here will be equal to 2 minus x. Now these two triangles are similar triangle. So we can use the property of a similar triangle. The height of this triangle is 1500, base is equal to x. Height of this triangle is equal to 4500 and base equal to 2 minus x. So this triangle I had drawn here separately. This point is same as point B. This point is equal to E. This point is same as equal to C. This distance is same as equal to x. E to C is same as equal to 2 minus x. This vertical height is same as equal to 1500, that is this height, and the height of this is 4500. So we can use the similar property. So we have 1500 divided by x is same as equal to 4500 divided by 2 minus x. 1500 and 4500, 3 is left. Now we can cross multiply. So we have 2 minus x is same as equal to 3x, that is we have 4x is same as equal to 2. So we have distance x is equal to 0.5 meter. 0.5 into 3000 is 1500, that is correct. In the first part you have to calculate the location. So this distance is same as equal to 2 meter. This distance equal to from B to point E is equal to 0.5 meter. It means that from point A the total distance equal to 2.5a. That is the choice B is correct. So in this case, the maximum bending moment will occur at point E, and the distance E is same as equal to 2.5 meter from A. That is equal to 2500 mm. So first part, our choice B is correct. So this value of x come out to be 0.5 meter. So remaining distance will be equal to 1.5 meter. In the second part, we have to calculate the maximum bending stress. That I will solve in the next slide. So this area will represent here the maximum value of a bending moment. So this one is maximum value of bending moment. So area will be equal to 1 by 2. Height is equal to 4500. And we have base is equal to 1.5 meter. So we have maximum value of a bending moment is 3375 Newton meter. We know the value of C, we know the moment of inertia, so we can calculate the maximum value of a bending stress. For this purpose, we'll use the flexure formula. Maximum bending stress will be either on the top fiber or bottom fiber. Since we are interested in the magnitude, so we'll use the maximum value of a bending moment multiplied by C divided by I. The I is the moment of inertia, BD cube by 12. Maximum bending moment is 3375, is Newton meter, is 10 to the power 3. C is the distance of the top and bottom fiber, that equal to 50. Whole thing is divided by BD cube by 12. This time the base is equal to 30, depth is equal to 100. So we have cube of 100 divided by 12. 12 will shift in numerator. So maximum bending stress here will come out to be 67.5 megapascal. 67.5 megapascal, choice B is correct. The maximum magnitude of a bending stress is 67.5 megapascal. This is another question appear in GATE 2018. We have given here simply supported beam of width equal to 100, height equal to 200 and the length equal to 4 meter. Carrying a uniformly distributed load of intensity 10 kilonewton per meter is same as 10 Newton per mm. Maximum bending stress you have to calculate. So UDL intensity is given as 10 Newton per mm. We have to calculate the maximum value of a bending moment first. Once we calculate the maximum value of bending moment, then you have to find out the value of C, that is the distance of the top fiber, which one is the same as equal to C. All bottom fiber is also equal to C. In the rectangular cross section, the distance C is remains same, and this value of C is same as equal to D by 2. Here we have base is equal to 100 and the depth is equal to 200. So either on the top or bottom we have maximum value of the bending stress. So we have 200 by 2, that equal to 100 mm. Next job is to calculate the reaction at point A and B. So for this purpose, we'll convert this UDL into equivalent point load. So UDL value will be same as equal to a W multiplied by L, where we have L is equal to 4 meter. So this value of W into L is 10 kilonewton meter multiplied by 4. That will be equal to 40, will be kilonewton. For finding the reaction here, we'll convert the UDL into equivalent point load. And because of a symmetrical loading here, we have equal reaction at A and B, that is 40 is divided by 2. So whenever we have a symmetrical loading, the reactions are equal. So we have AY is same as equal to BY is 40 divided by 2. So we have 40 divided by 2. So each of the reaction here equal to 20 kilonewton. So this reaction is 20 kilonewton, as well as this reaction is also equal to 20 kilonewton. If you remember the maximum bending moment formula for the UDL is well and good. Otherwise you can construct the SFD. At point A we have vertical load acting is 20 kilonewton. So we'll move vertically upward at point A and we'll represent here the shear force equal to 20 kilonewton. Now for drawing the SFD you have to consider the UDL, that is a rectangle. If it is a rectangle in the load diagram, then we have a triangle in the shear force diagram. Here the total load is equal to 40, so we have 20 minus 40. So we left here with minus 20 kilonewton. And at point B we have reaction equal to 20, so we'll close at 0. So this one is a positive value and this one is negative value of shear force diagram. Because of symmetry here, the point C we can locate comfortably. This distance is same as equal to 2 meter as well as this distance equal to 2 meter. Since we have the change in the shear force sign at point C, so maximum bending moment will be at point C. So either you can take this area, which one is the area of triangle, or you can take this area is one and same. So in this case, the maximum bending moment M max will occur at point C, and this value is same as the area of triangle, which one is 1 by 2. We have height is equal to 20 kilonewton and the base is equal to 2. So 2 and 2 will cancel out and we have maximum bending moment equal to 20 kilonewton meter. And finally we'll use the flexure formula to find out the maximum value of a bending stress, which is same as equal to maximum value of a bending moment multiplied by C divided by I. Maximum bending moment is 20 kilonewton meter is 20 into 10 to the power 6 Newton mm. C is equal to 100 divided by BD cube by 12. This time we have base is equal to 100, depth is equal to 200 and we have cube of depth. 12 will shift in numerator. Solve this, you will get the maximum value of a bending stress. So maximum value of a bending stress here will be equal to 30 megapascal. The video you are watching is from the app, which is the More Class app available on Google Store. And in this app, we'll cover all subjects involved in mechanical engineering for GATE. Join the course directly from your mobile. The link is given here.